Hello, everyone. I'm making some short videos for you to help with sections 5.4 and 5.5 for the fundamental theorem of calculus. This one's going to go through 5.5 significantly slower than we did in class because we had to go so fast. But basically, 5.5 is the second part of the fundamental theorem of calculus. And the second part of the fundamental theorem of calculus creates this area function. And basically, an area function is a function of x, but what our variable x is actually the upper bound of our interval. So what we're doing is we are fixing some a value here. Let's say a equals 2 up here. We're fixing a starting interval of 2, and we are letting the end of our interval be x. And so wherever we want our area to end, that is going to be our variable, so that we can basically find areas underneath one function quickly over and over again without having to redo a bunch of integrals. We're going to integrate once. We're going to get an area function where when we plug in the right side of our area, of our interval, we get area out from our a value down to our x value. We kind of went through that in class, but this area function, it's an integral with a variable in our bounds. And that sounds a little scary, but honestly, it's a definite integral, and we are going to evaluate it just like a definite integral. But the cool thing that the second part of the fundamental theorem gives us is that this area function is an antiderivative of this little function inside. And that should make sense because to evaluate this definite integral, you're going to find an antiderivative of it and then plug your bounds x and a in, and you're going to have an antiderivative. And so this area function is an antiderivative of our little f here, and that means that the derivative of our area function gets us back to little f. That's what it means to be an antiderivative. And so because a prime equals little f, what that means is if I take the derivative of this integral, right, this is our area function, a of x, if I take the derivative of that, I get right back where I started. But what that really solidifies for us is that a derivative and an integral are inverse operations. They undo each other. The derivative of an integral gets us right back where we started. We just have a little bit of a variable swap because in this process we'll plug x in. And I'll show you what that looks like in just a minute. We'll go the long way and actually find one of these area functions so that you can see it. But for now, what I really want you to get out of this is that integrals and derivatives are inverse operations. They undo each other, which shouldn't really be a surprise to you at this point. I think we've really kind of we've been doing this enough and we've talked about this enough that I think, an integral is an antiderivative and a derivative goes the other way, right? So an antiderivative takes you from your derivative to your OG, and a derivative takes you from that OG right back to your derivative. So yeah, they're inverse operations. So we didn't really get to do many of these in class, but I also think that we've kind of done this already. So we just haven't put it in this notation. So let's say our area function fixes the starting value of my interval at 2, and my variable x here is the top bound of this area. That's where my area ends. And so that's what my area function looks like. It's the area underneath little f of t, which is this graph over here, from x equals 2 to x equals whatever my variable x is. Okay, so what if I want to find a of 4? Well, that means that x equals 4 in this one, and that means that my area function, because of how it's defined, this is finding the area from x equals 2 to x equals 4 of f of t dt. Well, we know how to do this. We've done this before. This is the area underneath my function from x equals 2 to x equals 4. Well, from 2 to 4, it's this area down here, which is 5. And because that area is below the x-axis, we're going to get signed area, which here, that's going to give us -5 because that area is below the x-axis. All right, how about a of 7? A of 7, again, this says x equals 7 here. So when I plug 7 into this function, this is going to be the integral from 2 to 7 of little f of t dt. So what's the area from 2 to 7? Well, it's going to be the area from 2 to 4, which we just found was -5, plus the area from 4 to 7, which is -11. So we're going to do -5 plus -11, and we're going to get -16. That's our area from 2 to 7. How about if x is 2? Well, that means that we're finding the area starting at 2, and my x value up here is now also 2, and so we're finding the area from 2 to 2 underneath this function. Well, if we start and end at 2, we have no area because our starting and ending points are the same. So that's a 0. And finally, how about a of 0? Again, we are plugging 0 in for our x. The 2 starts where it is down here, and we end at 0 up top. Just plug it in. I realize that this is backwards. These are going to be those weirdo places where this is how we get one of these upside down integrals. And so we have to evaluate it in the form that it's written. So if we want the area from 2 to 0, because these are upside down, this is going to be the negative of the area the right way, from 0 to 2. That was one of our linearity rules from 5-2. And so the area from 0 to 2 is right here. It's 8. And so it's going to be the negative of that. So this is going to be -8. Again, I know that area is positive, but because our bounds are upside down and we are going backwards, that basically makes our area negative now. Okay, so hopefully we were primed for that from section 5.2. It's an area function. You're just going to plug those in and find the areas that it's telling you. Now, what if instead of having a graph with areas, what if I'm given a function? And here my function looks like 1 minus 6x minus the cosine of x. Ugh, and I have no idea what that looks like. So we aren't going to have a graph for this. We're going to have to do this algebraically. And we want to fix our a value, our starting, the starting point of our interval at -pi. Well, in that case, our area function looks like the integral from a to x of our little f of t dt. So what that's going to look like is that our area function is the integral from a. We are fixing our a, our starting value, at -pi, and we are ending our area at whatever our variable x is. And we are going to integrate this function little f. But again, notice the variables. We're going to be careful with the variables. In here, we need to pick a variable that's not x, because technically this variable in our outside function x is already up here. It's in my interval. I need to pick a different variable in here so that I don't get confused. So we're going to do t's. So my function is going to be 1 minus 6. I'm using a variable of t, and I didn't leave myself enough space, minus the cosine of t dt. So this is what my area function looks like. Okay, so how am I going to find my area function from this? Well, don't panic. This is a definite integral, right? I've got an integral with bounds on it. It's area. So how do I find area in definite integrals? Because again, I don't know what this looks like. I can't graph this. I can't do it with geometry. We're going to do it with calculus. So fundamental theorem of calculus part 1 says, go ahead and take the antiderivative. So to take the antiderivative of this, we are going to have t minus, I'm going to increase my power by 1, divide by that new power. And the antiderivative of cosine of t is sine of t. And I'm going to keep that sign of negative, of this negative, right? The derivative of sine is cosine, so I'm going to keep that negative here. And I can choose any antiderivative that I want with a definite integral. So I'm going to pick one where c is 0. And then I need to evaluate this from negative pi to x. Okay, and then now this notation says go ahead and plug your bounds in. So I'm going to just do that. I'm going to plug x in for all of my variables that are t's. So I'm going to get x minus, I'm going to simplify, 6 divided by 2 is 3. I'm going to plug x in for that t and get x squared minus the sine of t, which I'm replacing with x. That's my top bound plugged in. And now I'm going to subtract negative pi plugged in. I'm going to get negative pi minus 3 times negative pi squared minus the sine of negative pi. And now we have to evaluate this. These, in this first one, they're all variables, and I don't have any like terms, so this is going to stay x minus 3x squared minus the sine of x. And now I'm going to distribute this negative and simplify all of this stuff. So minus a negative pi becomes plus pi. This negative pi squared becomes positive pi squared. When I multiply by negative 3, it's negative 3 pi squared. And then when I distribute this negative, it becomes plus 3 times pi squared. And then the sine of negative pi goes this way, but we're still over here. My ordered pair there is negative 1, 0. So the sine of pi or negative pi is the y value. It's 0. So that's going to be 0. Negative 0 is still 0. If we distribute that negative, still 0. So I'm not going to bother writing that. It's just 0. And no like terms to combine. This is, in fact, the end of the line. Notice this is a function of x. The only variable you see here is x. I know we started with t's, but once we evaluated our bounds and plugged our bounds in, we got x's and numbers, and that's it. So now this function has x's in it. And if I took an x value and I plugged it in, what I would get out is the area from t equals negative pi to t equals whatever value I plugged in. And that would be the area underneath the function y equals 1 minus 6t minus the cosine of t dt. That's what we would get area for. So if I plugged in x equals pi, I would get the area from negative pi to positive pi underneath whatever this function looks like. This is the area that I would get if I plugged pi in for all of these x's. It would give me area out, which I think is cool. And notice this area function, this should be an antiderivative of my little f, right? That's what this fundamental theorem says. It says that that should be an antiderivative of what I started with. Is this, in fact, an antiderivative of what I started with? Well, I don't know. Let's do this part and show that that's true. Let's take the derivative of this. So I'm going to switch colors here so that we can kind of see this. What is a prime of x? What's the derivative of this whole function? Well, the derivative of x is 1 minus the derivative of 3x squared. I'm going to bring the 2 down, and I'm going to have a 6. And then I'm going to subtract 1 from my power, and I'm going to get 6x to the first. Minus the derivative of sine of x is the cosine of x. The derivative of pi, yeah, that's 0 because it doesn't have a variable in it. Plus the derivative of 3 pi squared also doesn't have a variable in it. That's a constant, so its derivative is also 0. So this is it. This is the derivative of my area function. And take a look and compare that to my original function that I started with here. It is the exact same thing. I just have x's instead of t's. And those x's came from plugging in that bound. So this verifies for us that the derivative of an integral does in fact get you right back where you started. We just get a little bit of a variable swap. All right, so if you have to find the area function, go ahead and just integrate it. No big deal. Okay, now what if we wanted to do something crazier? What if we want to find the derivative of this area that represents an area function? Well, because we're taking the derivative of an integral, and I know right off the bat, I'm taking the derivative of an integral. I don't have to go through this whole process that we went through up here. I don't have to take the long way and find the antiderivative and then plug in my bounds and then take the derivative because I already know what's going to happen to this. The fundamental theorem part 1 says the derivative and the integral are going to undo each other. They're inverse operations. The derivative is going to undo that antiderivative. I'm going to end up right back here, but I'm going to get x's instead of t's. So I'm going to get x squared plus x minus 1. And I won't have any plus c's because, again, with a definite integral, you don't have plus c. You don't have to worry about it. Cool. I've also had questions before with, does it matter what this bottom bound is? And the answer is no. It doesn't matter whether this is 0 down here, or whether it's 3, or whether it's 37, or whether it's negative pi like it was here. Because no matter what that bottom bound is, after you plug your bounds in, the part that came from that bottom bound was here when we did this example up here. And notice if we evaluated this integral and plugged our bounds in, the part that came from this bottom bound is going to be a number. And then when we do this derivative on the outside, the derivative of the number part goes away and it goes to 0 anyway. So it does not matter what that bottom bound is. It's not going to affect this process in the least because it's going to go away with that derivative on the outside, so we don't have to worry about it. All right, so let's try this next one. This is asking me to find g prime of s. And it's telling me that g of s is the integral from 0 to s of sine squared of t dt. Well, g prime of s, that's a derivative of g of s. So really, g prime, here, I'll write this down here, that way it makes a little bit more sense. G prime of s, which is what I want, that's the derivative of g, which is this function right here. So I'm taking the derivative of an integral. What's going to happen when I take the derivative of an integral? Yep, they're going to cancel. I'm going to end up right back here, but I'm going to get a variable swap, and my variable is going to become whatever is up here, and I'm going to get sine squared of s. And that's what's going to come out of here. I don't even have to go the long way. And here we actually don't know how to integrate sine squared, but that's okay. We don't need to. We can just take the fundamental theorem, and say thank you very much. Okay, what if, one last challenge problem, what if it's not just a variable by itself up here? What if I put like a whole function of x up here? What if I have stuff up there? What happens then? Well, in order to figure this out, we are going to take the long way so that we can see what happens when this is not just an x up here. It's a whole function of x. So to do the long way, we're going to start on the inside and we're going to evaluate this definite integral. So we're going to let the derivative hang out here. That's a problem for future us. And then we're just going to evaluate this noodle in here. The noodle says find the antiderivative. What's the antiderivative of sine of t? Yep, it's negative cosine of t. And this is a definite integral, so I don't need a plus c. I need the evaluation notation. And now I'm going to plug those bounds in. And when I do that, I'm going to get negative cosine of 5x to the third minus negative cosine of negative 2. Are you okay if I do a minus a negative cosine? That's going to turn into plus the cosine of negative 2. Okay, I'm not going to bother simplifying this anymore. Now let's actually do the derivative part of this. We're going to take the derivative of each of these. Okay, so we're going to take the derivative of negative cosine of 5x to the third. How do we take the derivative of negative cosine of 5x to the third? Yeah, that's a chain rule. So you're going to have to do your outside function and your inside function. My outside function is negative cosine of x. My inside function is 5x to the third. The derivative of my outside, the derivative of negative cosine of x is negative sine, which is going to be a positive sine of x. And the derivative of g, my inside function, is going to be 15x squared. And so I'll plug g into f prime, and I get the sine of 5x to the third times g prime of x, which is 15x squared, plus the derivative of the cosine of negative 2. There's no variables in here. This is a number. The derivative of any number is 0. So this is my final answer. The sine of 5x to the third times 15x squared. Okay, now let's think about, I'm going to erase this just for a second because I want a little bit more space here. Let's generalize what just happened here. Take a look at what we got out of this and take a look at my original stuff and my original function. What do you notice? Yeah, we basically can just take my stuff and plug it into my function, just like we did up here, right? We took that variable up here and just plugged it in. But now, because this is not just a variable, it's stuff, we then have to do the chain rule and multiply by the derivative of that stuff up there. So if you don't have just an x up there, if you're integrating a number to some stuff, I'm going to say little f of t dt, and then we're going to take the derivative of all of that. What you're going to get, it's going to be the derivative and the integral are going to undo each other, and you're still going to end up back at this function with your stuff plugged in. We're going to get f of our stuff, and then we just have to multiply by the derivative of my stuff because chain rule. That's what's happening here. Okay. And I'm just going to try to make this, oops, my bad, a little smaller so that I can still read the next problem. So this is how we're going to deal if we have stuff up here. Okay, so this says I want to find g prime of x, given that this is what g is. Okay, well, g prime of x, this is the derivative of g. And g is this integral from 2 to x squared of e to the p over p squared dp. This looks really scary, and I couldn't integrate this. We don't have the tools that we need to integrate that. But the good news here is that we don't have to integrate because I'm taking the derivative of an integral. We know that the derivative and the integral are going to cancel out, and I'm going to get back here to this function, but with this plugged in. So what I'm going to get out of this, we're going to replace every p, every variable here, with x squared. So I'm going to get e to the x squared over x squared squared. Plug it in for each p. That's the f of my stuff. And then don't forget to multiply by the derivative of your stuff, the derivative of whatever's up here. The derivative of x squared is 2x. That's what's going to come out of this. And we can simplify this a little bit. I'm going to get e to the x squared over x to the fourth. And I'm going to multiply by 2x. Technically, this is like over 1. So this x is going to cancel one of these, and I'm going to have 3 left. And so overall, this is going to give me 2e to the x squared all over x to the third. That is what I'm going to get out of this. We didn't have to do an integral followed by a derivative. We just know that the derivative and the integral are going to cancel out. We're going to plug that bound in, and then if it's more than just an x, if it's a stuff, do the chain rule and multiply by the derivative of your stuff on the outside. All right, that was a much more in-depth version of 5.5. So I wanted you to have that because I know we had to go super fast through that. Some of you won't need all of this, but I wanted you to have it in case you needed it. So to find an area function, right, your area function is this definite integral from a number to an x. If you're finding the area function itself, do the definite integral just like before. Antiderivative, plug your bounds in. Your bound is going to be a variable. Don't panic, just plug it in. But if you are taking the derivative of your area function, right, the derivative of an integral, that's when they're going to cancel out and you're going to get right back to your original function. All right, so go ahead and wrestle with those. Let me know if you have any questions, and I will see you next time.